All right, how's it going, everybody? We are here on Tuesday of week 14, and we're going to talk section 11.6 today, absolute convergence and the ratio and root tests. We'll also see some examples at the end that will kind of be my sort of representative of a little bit of 11.7 out there. I think that you guys are certainly capable of reading these suggested strategies associated with testing in 11.7, but we will see sort of a spread of problems that we'll solve using different techniques here today. So in a sense, that's so we're going to be encapsulated there. So in section 11.6, we're going to talk about absolute convergence, and we're going to be getting two new tests, the ratio and the root tests. The ratio and root tests are each the proofs of the ratio and root tests are both dependent on a theorem associated with absolute convergence, which is why these are related here. So what we kind of want to ask ourselves is, why is there still more stuff for us to talk about? Like, how do we even know like what the next direction to poke around is based on what we've seen so far? So let's look a little bit at a sort of summary of what we've seen so far and kind of ask ourselves, what series are we still not capable of talking about? We want to kind of say, what have we done? And therefore, what haven't we done? That's kind of what I want to look at first here. So again, our goal is really just to be able to decide, does this series converge or diverge? And we've been looking at this for quite a few sections so far. So one of the first things that we looked at for convergence of a series back in section 11.2 was talking about geometric series. We saw that geometric series are always of the form a times r to the n minus 1. And we determined that these are going to be convergent series if that common ratio r has a magnitude less than 1. But if that common ratio r is larger than 1, then we're going to diverge. And in fact, the one special thing actually about this one is that it's the one scenario in which we actually know what we converge to. In all of our other tests, we just determine we've converged. And so this one's a little bit special in the fact that it's the one scenario in which we can say, hey, I know exactly the value of our convergent series. Then again, these are relatively rare as far as all the series go that are out there. So very good for comparisons, but not necessarily to be expected that we'll see these guys. Next up, we saw our test for divergence. This one will be important. We'll see this one come up today. This is kind of, in a sense, our most basic test for convergence, divergence here. I guess this one will only tell us about divergence. This says if this unknown series is convergent, then it's going to be the case that the limit that's not our test for divergence. A general statement is, if the series is convergent, then it is the case that the limit of the sequence associated with the series is going to be equal to 0. Our test for divergence says, if a limit of those terms of a sequence doesn't exist, or if the limit of the terms of the sequence is not equal to 0, then the series must be divergent right there. So that's our test for divergence. If the limit of the sequence, the associated sequence, doesn't exist or is not 0, then the series is going to be divergent. Remember, we've got a little bit of a distinction between sequence and series happening there. Next up, we saw the integral test. We kind of looked at all those Riemann sum type pictures out there with that very nice Desmos graph, and we saw that we can use integrals to, in a sense, bound the values of our series here, and therefore we can make judgments that say things like, if the integral of the related, if we can make this relationship between the terms of a sequence and a function f of n, if we can do that, then if the integral from 1 to infinity of that function, if it converges or diverges, then the associated series will also converge or diverge. They will kind of have matching convergence right there. The next thing that we saw from this was this idea of p-series here. This was sort of related to our idea of looking at that harmonic series and sort of related to our ability to judge this with the integral test here. Any series that is of the form 1 over n to the p is going to converge if p is strictly larger than 1. Remember that this or equal to right here, if p is equal to 1, then we're the harmonic series. That's one that we for sure know diverges. We know it diverges by the integral test. I'll in fact do that one again here in a second. But p-series are kind of related to our geometric series. They're kind of the series that we are, in a sense, the most confident in. It takes the least work for us to for sure know what's going on with that series. After we saw the p-series, we saw the comparison test. This was what we looked at in our video yesterday. And very importantly, the comparison test has this requirement that says all the terms in each of the series that we are comparing have to all be positive for us to be able to apply the comparison test. The comparison test just says if we can find a series that converges and the terms in our series of interest are all less than the terms in the convergent series, then our series of interest will also converge. And conversely, if we have a comparison series that we know diverges, and if all of the terms in our series are individually each larger than the terms in the known divergent series, then our series of interest, A sub n, must also diverge. That's our comparison test that we looked at in the last video. We also saw the limit comparison test in the last video, and very importantly, the limit comparison test also requires all positive terms. The limit comparison test says if we have two series, A sub n and B sub n as series, then we have that the limit of the ratio of their nth term. If it is equal to a positive constant, then either both series converge or both series diverge. This is still a comparison. We're still thinking to ourselves there is a series that we want to know about, A sub n. There is a series that we already know about the convergence of, a B sub n series. Then we can compare the ratios of their terms, allow the limit as n goes to infinity. If we converge to a positive constant, then either both series converge or both series diverge. So another comparison that we made there. Next up, we looked at the alternating series test, and notice that this one has a requirement about sign as well, right? And kind of, I'm trying to, in a sense, trying to emphasize this to you right now on the screen, right? There's these requirements about the sign associated with each of the terms in our sequences and series here. So this alternating series test, this requires us to alternate sign each term, right? This isn't just about series that have positives and negatives. It has to be positive, then positive, then negative forever. It has to be alternating sign every single term for us to satisfy the conditions of the alternating series test. If we do have an alternating series, then it can be written in this form with that -1 to the n or to the n plus 1. I'm not really too worried about what our choice is up there in the power as long as it results in that alternating back and forth sign. Then if we can show that each consecutive term's magnitude is smaller than the previous term's magnitude, and if the limit of the magnitudes goes to 0 as n goes to infinity, then we'll know that that alternating series is going to converge. But again, it's got this requirement about the signs associated with these things. So here's what we've kind of seen. So far, every rule that we've had requires either for us to have all positive terms in our series or terms that alternate every sign. So kind of what I'm thinking to myself here is, what series haven't we talked about? Well, we haven't talked about series that have negative terms, and we haven't talked about series that don't have necessarily like a pattern to their positives and negatives out there. Now, the good news for us is that one of those is easily manageable. All of our tests that require us to have all positive terms are in a sense covering for us the scenarios in which a series has all negative terms, because if that is a common factor of a -1 that's being included in every term, then we could factor that out in front of the series, that we would just have -1 times a series that has all positive terms. And therefore, all of our positive term requirement tests could then go ahead and apply to that series that has all negative terms, because we could just factor out that negative right there before we go ahead with our analysis, right? So that's kind of saying to me, all positives are handled, all negatives are handled, alternating positive and negative is handled. So it seems to me like the one case we haven't really discussed yet is what happens when we have series that don't necessarily have a specific pattern to their positives and negatives, where there might just be some sort of intermingling of positive and negative terms. That's what we're seeing here. Therefore, the types of series we haven't discussed yet are series that have both positive and negative terms, but don't necessarily alternate in sign every single term. So what we're going to do is we're going to define a new idea here and see kind of where it takes us here. And this is going to be our idea of absolute convergence. We say that a series, a general series defined by terms A sub n, is absolutely convergent if the series where we're just taking the absolute value of each of the terms converges. All right. So what we're saying here is we're not, notice, I think just the one thing to point out here is the absolute value bars are on each individual term, not outside of the sum. It's on each individual term. So we're taking the absolute value term by term, not computing the whole sum and taking its absolute value. All right, that's just our one kind of distinction to make right there. So let's look at two quick examples and talk about their absolute convergence. The first example that we can look at here is this is our alternating 1 over n squared series right here. So we've got our alternating term out front, -1 to the n plus 1 power, and we've also got 1 over n squared. So we're going to get these fractions of 1 over n squared, but we can see we're getting positive, negative, positive, negative, positive out there. So one thing I could do is I could go ahead and I could look at what's going on with the sum of the absolute value of -1 to the n plus 1 times 1 over n squared. And what I can see here is the absolute value associated with this -1 to the n plus 1 is essentially just going to eliminate this. This is just going to say, listen, I don't care if you're giving me positive or -1s. Absolute value says make them positive. I can also see here 1 over n squared. That's also guaranteed to be a positive term all the time anyway, even if we had negative n's, which we don't. We're plugging in all positive n's. So it's not even positive because we're squaring. It's really positive because all of our n values are positive that we're interested in applying to this guy here. So it seems like the absolute value of each individual term of this series is really just going to bring us right back to a series that we already know, 1 over n squared. We know that this converges. It's a p series with p equals 2. And therefore, I can make two statements here. One thing I can say is I know that this series is going to be absolutely convergent because I took the absolute value of each individual term of the series. I recognized that that just made it equal to a series I already knew about which converged. So I showed that the series where we're taking the individual absolute values of each term converges. Therefore, the original series is what we say as absolutely convergent. Here's the other thing that I know about this one, by the way. I can see that this is an alternating series. I can also see here, I'm going to go ahead and grab our, let me write it like this here. Let me get this guy. Remember, this is like our b sub n term that we identified yesterday right there. So I also can see here that b sub n plus 1 is less than or equal to b sub n. I can see that as 1 over n plus 1 squared is less than or equal to 1 over n squared. That's definitely always true. I can also see that the limit as n goes to infinity of b sub n is the limit as n goes to infinity of 1 over n squared. And that's equal to 0, which is all the other condition associated with the alternating series test. So I'm also noticing that by the alternating series test, this sum of -1 to the n plus 1 times 1 over n squared is just convergent, right? So we determined absolute convergence by looking at the absolute values of the individual terms. Yeah, don't worry, Coffee Gopher. We'll be there on the very next page. Yeah, I totally agree with you on this one right here. We will fumble with our words in this section. It is going to happen. Right? So we checked two different things right here. Right? One thing we checked is if I take the absolute value of each individual term, does it converge? Taking the absolute value of each individual term just turned this into the series just regular old 1 over n squared, and that converges. Therefore, the absolute value of each term converges. So we call this thing absolutely convergent. The other thing that I can see is that without taking any absolute values, I recognize this series to be an alternating series, so I hit it with the alternating series test. The alternating series test had both of its conditions satisfied, so I also just know that it is just regular old convergent by the absolute, or by the alternating series test. And not only that, now my acronym, I need to, A there stands for alternating, not absolute. Okay, all right, so there's one example right there. What we can see in this example is this alternating series of 1 over n squared is both absolutely convergent. It is also regular convergent. Let's look at another example now, see these things continue to be related here. So I'm looking now at, so by the way, I'll scroll back up one more time here. Notice that these are like almost the same example here, right? The only difference is this has n being squared and this does not have n being squared. This is now our alternating harmonic series. Right? This is the harmonic series, but we're going to alternate sign. All right, so I could ask myself, is this absolutely convergent? That's my question. And so I'm going to look at the absolute values of each of our individual terms here. We're going to get the same type of result right here, which is that our alternating stuff is going to, in a sense, go away. That's what the absolute value is going to handle for us here. So this is just going to become this sum, the harmonic series, right? That's what happens when you take the absolute value of all these terms. All the negatives are now positive. Now we just have the straight up harmonic series, and this diverges. I'll just say it's a P series, P equals 1. So this is not absolutely convergent. Not absolutely convergent because if you take the absolute value of each individual term and then try and add it all up, you get the harmonic series. And the harmonic series diverges because it's a P series of P equals 1. But the other thing I'm noticing is that this is an alternating series, right? I am noticing here that b sub n plus 1 is definitely less than or equal to b sub n in all cases because we just have 1 over n plus 1 is going to be less than 1 over n in each case. And again, we're identifying this guy right there as our b sub n right there. I also can clearly see that the limit as n goes to infinity of b sub n is going to be the limit as n goes to infinity of 1 over n, which is 0. So that does satisfy both conditions of the alternating series test. So it seems like this series, negative 1 to the n plus 1 of 1 over n, is convergent. So before we go on to the next page, just want to kind of like highlight what we just saw right here. In the first example, we saw that the alternating series of 1 over n squared was both absolutely convergent. You could take the absolute value of each term and it would converge. Or you could just leave it alone, positives and negatives, and it's also going to converge by the alternating series test. Then we looked at the alternating harmonic series right here, and we saw that if you take the absolute value of the alternating harmonic series, it just becomes the harmonic series. The harmonic series diverges. So this thing wasn't absolutely convergent. But we did find that if we use the alternating series test, since we do have decreasing magnitudes of terms, and since the limit of the sequence associated with the magnitudes does go to 0, that this will be a convergent series right here. All right. So what we're kind of seeing here is that sometimes you are both convergent and absolutely convergent, but not always. Right? What we're going to end up claiming here. Oh, sorry. Let's define this. This is referred to, what you're seeing on the screen right now is called conditional convergence. It's when we have a series that converges, but if you were to take the absolute value of each of the individual terms, then it no longer converges. So that the negatives contribution, when you make it positive, that's enough to push us over the edge to diverge off to infinity out there. So conditional convergence, again, is when the series does converge, but if you were to take the absolute values of each term, it no longer converges. It doesn't experience absolute convergence. We're definitely seeing this in this alternating harmonic right here. So this is conditionally convergent. I'm going to point out to you that, and man, this is going to be one of those things where I feel like I occasionally throw in some like interesting tidbits into here. This is one of the most into this class in general, kind of sticking in some other topics in here. This is one of the weirdest things that we can ever see associated with sequences and series here. There will be a very, very strange idea associated with conditional convergence that I'll talk about at the end of this video right here. Conditional convergence can cause some really weird things to happen. And ultimately, it's going to remind us what we're going to see at the end here when I see this really weird conditional convergence stuff is it's sort of a reminder that even though we're trying to use lots of finite sum techniques to help us think about infinite sums, there is definitely still a gap between the idea of finite summation and infinite summation that we can't quite just bridge with a bunch of logic arguments right here. There's still an objective difference between those two. And so we'll come back to see this kind of really, really weird thing happen at the end of the video right here. I want to like kind of get through some more topics and do some examples before we see the strange stuff that's difficult to explain. So in any event here, that's just a definition for us right there. Conditional convergence, it's when you do converge, but not if you take absolute values of each individual term. You're not absolutely convergent. So a very important theorem that's what we're dependent on to prove both the ratio and the root tests that we're going to get in a minute is that if a series is absolutely convergent, then it is regular convergent here. And real quick, just notice up here, This guy was absolutely convergent, and it was convergent. So that agrees with our theorem. This guy was not absolutely convergent. So it didn't guarantee for us that it was going to be convergent. It turned out that it was, but we didn't get this from that theorem we just stated down there below. If the series is absolutely convergent, that will guarantee for us that it is convergent without the absolute values out there as well. So let's talk about why this one's true. This is a pretty cool little proof of just using some of the ideas that we've seen before. This proof is the more manageable one of the ones that you'll see in the section out there. The ratio test proof is a little bit hairier. The root test proof is left as an exercise, which I think is a little bit funny. It's not unmanageable, but it's a little tough out there. So let's take a look at this. How do we know that this statement is true right here? If a series converges absolutely, then it is convergent without the absolute values. All right. So we're going to start by supposing exactly what this says. If a series is absolutely convergent. So that says to me, suppose A sub n is absolutely convergent. That's our hypothesis to the theorem right there. And what do we mean when we say that something is absolutely convergent? What we mean is that if we were to take the sum with absolute values of the individual terms, then that would converge, right? So this is sort of our base statement that we're working from. A sub n is the series of interest. We know that the series associated with the absolute values of A sub n's is convergent. Now, one sort of simple statement I can make here is that if a series is convergent, then it must be the case that 2 times that series is also convergent, right? We converge to a number. This one's just going to converge to 2 times whatever that number is. There's never a case where multiplying something by 2 causes it to go from being finite to being infinite, right? We can always just double whatever value we got from this convergence. We're going to use this fact right here, along with a little bit of a comparison test to arrive at our desired result, that the original series, just the straight up A sub n series, must be convergent. And here's how we're going to do it with the help of this relatively simple inequality here. Notice in this inequality, all we're really saying is, I think this one's pretty straightforward. Either it's going to be the case that an individual term A sub n is positive or negative. If A sub n is negative, then what we're going to see here is that this will be the positive version, this will be the negative version, and we'll get 0 for the middle term. 0 is less than or equal to 0 is less than or equal to 2 times whatever the positive version was. That's definitely going to be true. On the other hand, if A sub n is positive, then in the middle here we're going to get 2an, and on the right we're going to get 2an, and we're going to get 0 down below, and since A sub n was positive, 2 times A sub n will be larger than 0, and so again the inequality is going to hold. So the way that you kind of justify this one for yourself is just kind of with 2 little branches. Suppose A sub n is positive. Then we're going to see that the middle term becomes 2an, just like the term on the right. On the other hand, we can assume if A sub n is negative, then the middle term becomes 0, which means it's just equal to the 0 that's on the left right there. And in either case, our inequality is going to constantly hold right there, regardless of whether or not A sub n is positive, negative, or 0, I guess. If it's 0, then it's just 0 is less than or equal to 0 is less than or equal to 0. So this inequality, not unbelievable at all, I don't think, right here. And what this inequality is doing is it's helping us set up a comparison test. We can see some comparisons that we can make right here. So here's what I know. We just determined that it's going to be the case based on our hypothesis here that 2 times the sum of the absolutely convergent series, or 2 times the absolutely convergent series, converges. Right? So I know that the series with terms that look like that converges. Therefore, there should be a series with terms that look like this that therefore also converges by the comparison test, because each of the individual terms is guaranteed less than or equal to each of the terms in a known convergent series, right? So I know that there's a series with terms A sub n plus absolute value of A sub n that also converges by the comparison test, is what I've just learned here. So that's all I'm saying in this paragraph here. This inequality helps us see that because this series is convergent, it must also be the case that this series with terms that look like the middle part of our inequality is also convergent by the comparison test, because each of these terms is guaranteed less than or equal to each of these terms. And if you add up an infinite number of these terms, we do converge. Finally, I can now say, since I know that this series is convergent, and since I know that this series is convergent, it must be the case that if you subtract one convergent series from another convergent series, you're going to get a convergent series. It's very similar to our argument that you can double a convergent series and remain convergent, right? So I'm going to do exactly that. I'm going to take the difference of 2 series that I now know converge. This one I know converges by the comparison test. This one I know converges because that was literally our hypothesis to the proof. We said, assume there's a series that's absolutely convergent. This is what we assume to be true. Notice here, if we perform this sum, this is really going to say that all of the a sub n terms within absolute value here are going to be exactly canceled away by all the terms in absolute value here, which is just going to leave us with the a sub n terms within our sum. Since this is the difference of two convergent sums, this therefore must be convergent right there. So it looks like knowing that uh, the absolute value series converges is a guarantee that the non-absolute value series also converges. So this is our just quick little proof that if a series is absolutely convergent, then it is convergent. So that says to us, you're allowed to just straight up, if you can just take the absolute value of each individual term and show that that series converges, then we know that we get convergence also for the original series that you were wondering about. So this is another way that we're sort of creating a different series other than the one in question. We're answering questions about this other created series, and we're using that information to push it back on the series that we had previously questioned. In a sense, this just feels to me like a different version of the comparison test because we're creating a new series that we can answer questions about, and then we're pulling that information back to the series that we were struggling to answer questions about. So it's not really a direct comparison that we're making here, but this is sort of our roundabout way of getting to the conclusions that we would like to draw. We're coming up with different series that we may or may not be able to for sure make decisions about, but if we can make the decisions about the made-up series, that information will directly relate to the information about the series we were interested in originally. So this is good. If a series absolutely converges, then it converges. But that doesn't go the other direction, right? We saw here, if a series converges, that doesn't necessarily mean it's absolutely convergent. So we saw that for the alternating harmonic right there. So here are some examples of series where we can more easily establish their convergence or divergence using this idea of absolute convergence here. So just a couple of quick examples before we see a couple more tests and do a bunch more examples right here. Here I can say, let's determine if this converges. Does it converge? It's a question mark, not an exclamation mark. Let's instead look at the absolute value of each of the terms. Well, again, all this absolute value is going to do is it's going to say, listen, there is no more positives and negatives. We're taking the absolute value of everything here. So that's just going to leave us with 1 over n cubed. This I know converges. This is a p series with p equals 3. So therefore, the sum negative 1 to the n plus 1 power over n cubed is absolutely convergent. So I'm wondering if this series is convergent. What I did to show that is I showed that in absolute value it is convergent. So I'm saying it is absolutely convergent. And what our theorem just showed us there is therefore the series is convergent. Right? So if we can show that a series converges with absolute values around all the terms, that guarantees that it will converge without the absolute values around all the terms right there. That's what we're getting from this absolute convergence theorem here. Similarly here, I can see a sum of cosine of n over n squared here. And what I'm kind of thinking to myself here is I can ask myself what's going on with, again, our absolute value series here. Now, what I know is that cosine of n is going to be taking on values that are between negative 1 and 1. Therefore, what I know is that in absolute value, it's really only taking on values between 0 and 1. So what I think I can do is I think that I can say that this is less than the sum of 1 over n squared and the sum of 1 over n squared converges. P series, p equals 2. Therefore, the sum of the absolute value of cosine n over n squared also converges by the comparison test. Therefore, we're going to get a string of therefores here. Oops, let me, oh, okay, risky. Therefore, I know that this sum of cosine n over n squared is absolutely convergent. And since I know it's absolutely convergent, it is convergent. All right, so a series of arguments that we're making here from one to the next to the next. So notice in this one, we used three different big ideas. I needed to use the idea of a p-series, I needed to use the idea of a comparison test, and I needed to use the idea that if we converge absolutely, then we converge in general right there, right? So that's really three different theorems that were associated with this one, but pretty easy, one to the next to the next to the next right there, right? Just remembering that cosine lives between -1 and 1 was all I really had to take me from this statement to this statement. We can see the easy comparison. We are less than a convergent series, so we can converge in absolute value. By the comparison test. If we converge in absolute value, we're absolutely convergent. If we're absolutely convergent, then we're convergent, which is what we originally wanted to know. What's up with the convergence of this sum right here? So sort of a string of arguments that we're making, but I think all of them were pretty easy arguments for us to go ahead and make right there. So the other thing that we get out of this absolute convergence theorem then is two more tests. And the proofs behind these tests are a little bit difficult. Definitely not beyond our reach here. The ratio test is proven by kind of creating a geometric series to compare against. The construction of the geometric series is kind of the and again, this isn't really that bad. You should not be intimidated by this proof right here. But it takes a good couple different logical steps for us to justify this. The good news for us, though, is that the ratio test and the root test are both very similar in practice. They both have very similar results associated with them, and they're both pretty easy to use and are associated with sort of two different contexts here. Okay. So let's kind of like look at these two tests here, the ratio test and the root test, and then we'll do a whole bunch of examples that involve these guys. The ratio test is going to say to us that we can look at it, for any series of this form. So one of the really important parts of the ratio test and the root test is there's no limitation on saying, oh, you need positive terms, you need alternating terms. It just says for a series of the form sum of a sub n, right? This is for any series, and that's what's good for us. What this is going to say to us is that if we look at successive terms of this series in absolute value, their ratio, if the absolute value of the ratio of consecutive terms in the associated sequence is less than 1, then our series is going to absolutely converge and therefore converge. I should say that right here. On the other hand, if the ratio of consecutive terms is a positive number larger than 1, or if this limit just diverges off to infinity, then we'll know that our series is going to also diverge. The one case that's not helpful to us here is if our ratio of consecutive terms in absolute value tends to 1, then our ratio test is going to be inconclusive. There's no information that we get out of this guy right here. So this doesn't say converges or diverges. This says go try another test if you end up finding that this will be equal to 1 right here. So when is this useful to us? Well, what you should be thinking to yourself is that if you're going to be using this ratio test, then you need to be able to perform, compute this limit. And this limit's going to be tough to perform if you can't do some nice algebra associated with these consecutive terms, this ratio that we're seeing right here, right? So in general, I like to think that the ratio test is good whenever we're doing lots of multiplication or exponentiation, because that's when I can take the ratio of some series and do lots of canceling top to bottom if we have lots of multiplication or powers going on. The times where I don't like using the ratio test is whenever there's lots of addition or subtraction or sometimes roots happening out there, especially if there's addition or subtraction under the roots. Because what we know is it's really hard to like simplify fractions if there's like a x plus 6 in the numerator or something like that. If you don't have the perfect factor to match it in the denominator, then you're not going to be able to do any cancellation there. So addition and subtraction terms make me weary about using the ratio test, but multiplication and exponentiation are good because we're looking to make a ratio of two numbers, and it's really nice if we can do some algebraic like canceling from top to bottom of this fraction that we see right here. And we'll see that happen in our examples coming up. The other test that we're going to look at here that's very related is the root test. And I can tell you, man, just like glance at these briefly, like without even reading them, like I literally was able to like copy and paste each of these things from one to the next statement because all of our kind of conclusionary things here are going to be very, very, very similar. This is still for any old series, and it's going to still be looking at the limit as n goes to infinity of the nth term of the series in absolute value here. But here we're going to take the nth root of the absolute value of the nth term in the series and let n go off to infinity here. Again, if we get a result that's a positive number, or if we get a result that's less than 1, then we are absolutely convergent and therefore convergent. If we get a result that's greater than 1 or tends to infinity, it's going to diverge. If it is equal to 1, then it's going to be inconclusive, no information. And it should also be pointed out, any scenario in which you get the ratio test to give you equal to 1, the root test will also result in you getting a result of 1. So when you get, if you attempt to use the ratio test and you find that your test was inconclusive, then you need to go try another test. And I can just say, don't go ahead and try the other partner pair right here because it will also give you something that's inconclusive right there. So it really means like another test, not one of these two, which sort of go hand in hand here. This series right here, because you're going to end up taking an nth root of a term right here, this is very helpful when our series contains nth powers so that they can be canceled with the nth roots. So these are just helpful in different sort of algebraic scenarios depending on what you want to do. If it's easy for you to take an nth root of the terms of your series, then use the root test. If it's easy for you to do cancellation top to bottom of a ratio of two terms in your series, do the ratio test here. If you've got lots of multiplication exponentiation, this is good. If you have powers of n, this is a good route to go for some of these things. So let's look at a whole bunch of examples associated with these guys. I've got a bunch of these here. These will take a little bit more room. I think I've got like 7 examples for us to look at. And then we'll come back and at the end, we'll look at this thing. What's so weird about conditionally convergent series? So that'll be our kind of last thing. But let's go ahead and hit 7 of these series right here and see what kind of things that we see here. So, and there's lots of different ways, by the way, that we can kind of go about some of these guys. The route that I'm picking is just, in a sense, the route that I'm picking for this one here, for each of these individual problems. So do recognize it's definitely going to be the case that there is always multiple routes to these guys, lots of different tests that we could possibly perform. So it might be that you think about this a different way, and that's completely okay here. So, first one that I'm seeing here, this series of negative 10 to the n over n factorial. What I'm seeing right here, the thing that's kind of jumping out at me is I see that we are only dealing with exponentiation in a numerator and multiplication in a denominator. Remembering that n factorial is n times n plus, or n minus 1 times n minus 2 all the way down to 1, right? Is the product of all integers up through n. That's our n factorial. So in a sense, this is really just a whole bunch of multiplication, right? That's negative 10 times itself, or n times. That's a product of n terms, 1 through n right there. That is a huge indicator to me that this should be a ratio test, right? So I'm going to say here, exponentiation, factorial is really just multiplication. Ugh. That says to me ratio test is probably good. So what am I going to do? Well, I'm going to recognize that this, come on pen, where'd you go? Nope. Am I losing my pen here? No, we don't do a hover anymore? Okay, okay, I can't really write it. Seriously? What just happened? Okay, looks like I'm gonna have to call the video for right now. And once I get my pen working, I'll post a second video of me walking through these examples.